Welcome to a deep dive into revolutionizing how we deploy Java microservices. For too long, setting up infrastructure has been a complex, time-consuming maze. If you've ever wrestled with configuration files, environment variables, and the sheer volume of infrastructure resources needed just for one Java application, you know the pain. Today, we're not just talking about automating deployments. We're talking about intelligently automating the very creation of your infrastructure as code, specifically tailored for your Java applications, using the power of generative AI. Traditionally, infrastructure as code, or IAC, has been our knight in shining armor against manual infrastructure provisioning. Instead of clicking through cloud consoles or manually configuring servers, IAC allows us to define our infrastructure, servers, databases, networks, and more, using configuration files. Think of it as writing a blueprint for your entire cloud environment. Tools like Terraform and AWS CloudFormation have become indispensable, bringing version control, repeatability, and consistency to our infrastructure management. This approach drastically reduces human error and speeds up the provisioning process, making our deployments more reliable and efficient. Now, let's zoom in on Java microservices. A typical Java microservice deployment isn't just one simple server. It often involves a Java virtual machine, JVM, a containerization layer like Docker, orchestration with Kubernetes, a robust database, PostgreSQL, MySQL, a message queue, Kafka, RabbitMQ, API gateways, load balancers, and intricate network configurations, not to mention monitoring and logging tools. Each of these components needs to be provisioned, configured, and interconnected correctly. The complexity multiplies with every new microservice and every new environment, development, staging, production, each with its unique configurations and requirements. Even with IAC, a significant bottleneck persists. Writing and maintaining these complex IAC templates for diverse Java microservices can be a monumental task. Developers often spend precious time crafting verbose Terraform or CloudFormation scripts, ensuring every dependency and specific setting is correctly captured. What happens when a microservice evolves, or a new dependency emerges? More manual updates, more boilerplate code, and an increased risk of configuration drift, where the actual infrastructure deviates from the intended code. This translates to slower innovation, inconsistent environments, and a drain on engineering resources. This is where generative AI steps in as a true game changer. Imagine a world where you simply describe your Java microservice infrastructure needs in plain language, or perhaps a high-level JSON specification, and an AI instantly generates the complete, optimized infrastructure as code templates for you. No more wrestling with syntax, no more hunting for specific resource properties. This isn't just about automation, it's about intelligent, dynamic generation, tailored precisely to your application's architecture and deployment environment. So, how does this magic happen? At its core, generative AI for IAC works by taking your high-level intent, whether it's natural language, a structured JSON, or YAML configuration, as input. The AI model, trained on vast datasets of existing IAC templates, cloud provider documentation, and best practices, processes this input. It understands the relationships between different infrastructure components, identifies the most suitable cloud services, e.g., AWS EC2 for compute, RDS for databases, S3 for storage, and then dynamically generates the full, syntactically correct Terraform or CloudFormation code. It's like having an expert infrastructure architect instantly translate your vision into deployable code. Let's walk through a practical example. Imagine you want to deploy a new Spring Boot microservice that requires a back-end PostgreSQL database, needs to be highly available, and should be accessible via an API gateway. Instead of writing hundreds of lines of Terraform, you might simply provide an input like, deploy a Spring Boot application on AWS, requiring a PostgreSQL database, an application load balancer, and an API gateway, with auto-scaling capabilities. The GenAI system would then interpret this, automatically selecting EC2 instances or an EKS cluster for the Spring Boot app, provisioning an RDS PostgreSQL instance, setting up an ALB, configuring API gateway endpoints, and defining the necessary security groups and networking, all within the generated IAC. The benefits for Java teams are truly transformative. First, deployment cycles are dramatically accelerated. Developers can focus on writing code, not on infrastructure boilerplate. Second, consistency is guaranteed. The AI adheres to predefined architectural patterns and best practices, reducing the chance of misconfigurations. Third, it significantly lowers the cognitive load for developers, democratizing access to complex infrastructure provisioning. Imagine junior developers being able to provision production-grade environments with minimal guidance, all while maintaining the highest standards of security and efficiency. Integrating this GenAI-powered IAC generation into your existing CI/CD pipelines is seamless. The process typically starts with a developer committing their application code and a high-level infrastructure specification. A CI/CD pipeline step then triggers the GenAI service, which generates the IAC templates. These templates are then validated, perhaps through static analysis tools or dry runs, before being committed back to a version control system like Git. From there, your existing CI/CD tools, like Jenkins, GitLab CI, or GitHub Actions, can pick up the generated IAC, run a Terraform plan or CloudFormation validate, and then Terraform apply or CloudFormation deploy, fully automating the provisioning of your Java microservice environment. While the concept is powerful, implementing GenAI for IAC requires careful consideration. Organizations need to define clear governance policies, including security guardrails, cost optimization rules, and compliance requirements, which the AI model must adhere to. Human oversight remains crucial. Generated IAC should undergo review and validation, especially for critical production environments. Furthermore, the ability to fine-tune the AI model with organization-specific conventions, custom modules, and preferred naming standards will be key to maximizing its effectiveness and ensuring it generates IAC that truly aligns with your enterprise architecture. Looking ahead, the convergence of generative AI and infrastructure as code points towards a future of highly autonomous cloud infrastructure. We're moving beyond mere automation to intelligent, self-adapting systems. Imagine AI not only generating IAC but also continuously monitoring the running infrastructure, identifying potential issues, self-healing, and even optimizing resource allocation in real time. This frees up engineers to focus on higher-level architectural challenges and innovation, truly elevating the role of the modern IT professional. The era of the self-aware, self-managing cloud is closer than you think. So, whether you're a seasoned DevOps engineer, a Java developer, or an IT student, understanding this paradigm shift is crucial. Generative AI for IAC isn't just a fleeting trend. It's a fundamental change in how we build, deploy, and manage our digital foundations. It promises to unlock unprecedented levels of speed, consistency, and innovation, especially for complex Java microservice ecosystems. It's an exciting time to be in tech, and the future of infrastructure automation is looking incredibly intelligent. Thank you for joining us on this deep dive. If you found this video insightful, please give it a thumbs up, share it with your colleagues, and subscribe to our channel for more cutting-edge technical content.